Hello everyone. So in the last lecture we are talking about the basics of computer organization. So we are trying to deal with a particular problem where we had a CPU, memory, and peripherals. Right? We had certain buses, right? So these are considered as the uh, lines or the connectors. We had typically the address bus, the data bus, and also another control bus. And we had like different connections among these circuit components. Right? For example, like CPU is actually connected with the address bus, and then the address bus is connected with the memory. Whereas if you look into the data bus, you have bidirectional connections, right? So, and also CPU sends control signals, and these control signals try to control these memories and the peripherals, right? After that, what we are trying to do is that we are trying to solve one particular problem where we had a CPU with 13-bit address, and then what we tried to do, we tried to interface 8 chips, right, of memory, where each chip had 2K addresses, and at each location I had 4 bit of data, right? And then we saw that how to interface those things, and from there we had introduced one particular concept of memory folding as well, right? So this, if you try to look into the memory, so we'll look into the peripherals in great detail, but after having some discussions about the microprocessor, the 8085 microprocessor, because as you can understand, the peripherals, there can be many different peripherals, right? So there can be display devices, there can be input devices like keyboards, right? There can be buttons and many things. So we'll look into the peripheral devices later. But before that, let us have a very brief discussion about the memories, because you'll see that there are different types of memories. When we try to talk about memories, you'll see that there are some external memories, and also there will be some memory in terms of the sense that it will store some data. Data means some instructions or some values inside the CPU as well, right? So we need to introduce them, because this distinction between the external memory and the memory that is inside the CPU, that it has a special name, we'll introduce it, but there is something, for now we are calling it memory. You can think it about, think it as an internal memory, but it also stores values. We need to introduce them for our understanding about the processor. So let us try to have a very brief discussion about the memories. Now, again, we'll revisit memory at the end of our discussion regarding the microprocessors. But for now, as I said, we need to distinguish between this and this, these two memories, right? So this external memory, this particular thing, let me just change the color. So this guy can be broadly divided into two parts. the ROM and the RAM. If I look into the RAM, typically RAM has different slots. We are talking about that, right? So in the last class as well. So if it has like M addresses or location, and at each location, if I store say n bits, so it's like M cross n memory that I'm dealing with, right? So this is my address, also known as location, and this is my bit weight. That means the size of the data that is stored at each slot or address or location, right? So what will be the size of my address line? Typically, it will be something like log to m, right? That many address lines in typical setup. Now, along with that, we should have the data line, right? Data bus. How many data lines should be there? I have n bit width, right? So I should have n data lines here. And along with that, I should have some external things, right? So to control this particular memory. So in the RAM, you will get three additionals, typically three additionals control lines or control points. One is read. That means this will be activated when you want to read the value at a particular slot. There is write. So activated when we want to write something at a slot. Okay. Now also we'll have something called chip select or simply a select line. So what is the purpose of the select line? To activate or select the chip. So again, apart from the address line and the data line, we have certain control lines, right? So I was mentioning here as well in the last class as well that there are many different control lines. We have a very simplified schematic, but depending on the device or the component that you are handling, there can be different types of control signals, right, and control lines. So here in the RAM, I have the read control, write control, because in RAM I can actually read and write both. And also I have chip select because it might be a case where I'm not actually dealing with this particular chip. We'll see one particular example as well. So there I need to turn the chip on or off depending on the signals that are getting generated from my CPU, right? So that's why there is a chip select line also in this particular component. Now, just a very quick note, as you have read in case of our, the logic gates and also like in our sequential circuits as well. So there can be a select, like there can be two different types of active lines, so active low or active high. So at this particular point, it might look very irrelevant because it's a very trivial thing, right? So it means that the chip, say probably we are talking about the chip selected. So active low means the chip will be selected if I send 0 in this particular line. And also active high means this particular chip will be selected if I send 1, which is a very trivial thing. I hope you have already read this. And probably you feel like this is kind of a very very naive or a trivial thing, right? There is no point to discuss this, and it's true. We'll not emphasize whether the chip is is activated by a low signal or a high signal, but you should be very very careful, because when you try to actually code or integrate different devices, you'll also see, like, while we'll try to write a code, it's very important to know whether you have an active low lines or active high lines. Otherwise, what will happen, whatever you write, your device will not work, because simply you are not activating it properly. So though it might look very simple thing, the problem is that you are not actually dealing properly with this particular device, right? Now what we'll do, we'll look into one again one component design, where it will be easier usefulness of this different control lines that we are talking about. Right? Before going into the discussion, I forgot to mention one particular thing. So in case of the ROM, which is, by the way, is nothing but read only memory, I need to change this schematic that I have drawn, right? So can you please pause this video and then can tell me what is the change, or what are the changes that I should make to this schematics to make it a ROM? So ROM means read only memory, as I am saying. So what is the change that I should make? Okay, so I hope you have tried to answer the question. So let me try to explain. So address lines, there should be address lines in ROM as well, because I need to pick up a slot, and also data line, because I have to read the data that is stored in that particular slot. Chip select, there can be many ROMs, among which I may have to select one particular ROM. So chip select line should be also there. Read, yes, because it's a read only memory, that means read operation is allowed, so the read line will be there. Write line, so it's read only memory, right? So there is no permission to write. So in ROM I cannot write anything, so write line will not be there in case of the ROM, right? So that is kind of a very basic difference between ROM and RAM. There are other differences as well, but for our purpose and understanding about the usability of these components, this is sufficient. So in RAM, we'll have the read and write both options available. So we'll have two control lines for read and write. Chip select is always there. For ROM, we'll only have the read line, but not the write line. So now we want to again have a design problem, because we want to just show you the purpose of different control lines, right? So we'll try to again have one design problem, try to address it, and then we'll have our understanding about these chip select lines. So we had used them in our last example as well, but just for the sake of discussion, let us have another design problem. And as I said, like, it's very interesting and important to understand that how we you know place these components in a particular design, because that is all about this computer organization is, right? So here we are trying to again solve one design problem, where we have total 8 KB ROM and total 16 KB RAM. The CPU that we are using, it has 16-bit address line. Okay, and um, we have some additional conditioning. So we we are defining that the ROM is starting at address location 0000. RAM is starting at address location 8000H. Okay. We also have this information that each of the memory chip is 4 KB with memory length 8 bit. Also, my CPU has 8 bit data line or data bus, and we have another conditioning that the respective chips are attached sequentially. Let us look into the problem. So I have total 8 KB of ROM, total 16 KB of RAM. I'm dealing with a CPU so, which has 16-bit address line. The ROM is starting at address location 0000H, and the RAM is starting at address location 8000. Each of the memory chip is 4 KB. That means I have so this means I have 2 ROM chip, right, and 4 RAM chip. Memory length is 8 bit. My CPU has 8 bit data line, right? That means at a time I can actually access one chip. The trick that we had used last time will not work. Now, first I have to check whether my CPU can accommodate all the sequential placement of these chips, right? So that we'll do. But before that, I have another particular point. The respective chips are attached sequentially. What does that mean? That means when I'm attaching ROM, so I'll place the first ROM, say ROM 1, and whenever I will reach the last address, the ROM 2 will start just after from that. Okay? So ROM 2 will be sequentially attached. Now, what about the RAM 1? So RAM 1, for that I have actually a different address. So whatever is that address, so I'll start with RAM 1. When I reach the last address for the RAM 1, after that I'll attach RAM 2. After that I'll attach RAM 3. And after that I'll attach RAM 4. Okay. So that's the statement. The respective chips are attached sequentially. Right? Now, let us see. I mean, at this point again, you have to pause the video and then try to answer whether you are able to design the diagram, and then we'll see that whether our diagrams are matching or not. So let us see. This, as I said, is the placement of my memory chip. So ROM 1. After that, I'll have ROM 2, RAM 1, RAM 2, RAM 4. Okay, just a quick point. You should not be confused when I'm saying that this when I reach the last address of RAM 1, after that I'll attach RAM 2. That means it's not physical attachment, by the way, right? So that means the starting address of RAM 2 will be just after the next increment of the last address of RAM 1. So there is no meaning of the physical positioning of your RAM 1, RAM 2 up to now, the problems that we are solving, right? That is also a problem of computer organization, the physical placements of these chips. But here, when I am saying that we are attaching RAM 1 after RAM 2, that means the addresses, right? It's not the physical placement. Though I am drawing like RAM 2 is just after RAM 1, I'm meaning I'm trying to mean that it's actually the addresses. So I finish my addresses allocated for RAM 1 here. Just after the next address, I'll allocate that address to the beginning of my RAM 2. So that is the meaning of the word that I'm attaching them sequentially, right? It's not a physical attachment. So with that notion, so this is my placement of 6 chips, right? 2 plus 4. Now I'll have my CPU, right? Okay. So if you see, I have mentioned that each of the memory chip is 4K, right? So if you have figured it out already, it should be like to the power 12 4K means. So I need 12 bits, right, to actually um, access these slots. So what I'll do, I'll take A0 to A11, and then I'll connect each of the chip, right? Now also for each chip, I should have the data line. It's bidirectional, but as I said, like even if I don't draw it with bidirectional arrow, you should understand that it's a bidirectional connection, right? Right. So it should be attached with my CPU. This is my bit. Right. Now let me try to allocate the addresses, right? So I'll do that here. So as I have already mentioned, my uh, starting location for ROM is 00008, right? So let me just to write it down in binary. So it's 0000 0000 000000000. This is my starting location for so first ROM starts. Right? So what will be the end address of my first ROM? As I have already mentioned, so 2K, right? So sorry, 4 KB number of addresses. So I need 12 bits. So I need to manipulate 12 bits here. So what will be my stopping address for ROM 1? It will be 00001111111111. Right? So that will be my stopping address for ROM 1. Right? So what will be the starting address for ROM 2? The ROM2 will start from just from the next address, right? So 0001 That will be the starting address of ROM2, right? What will be the end address of ROM2? So my end address of ROM2 should be 0001. Now again, I need 12 bits, right? So 1111 1111 1111 4. This will be the right. So again, you have already learned that I can actually use a code to force that when I get any number between like 000000000000000 to 00001111111111. By the way, as you can see that it's very inconvenient to speak the binary digits. That's why we use the hex digits, right? So it's like 00008, and this is your 0 f f f. Okay? So any number in between that, you can force your code to select ROM1, right? But as we have seen, there are certain issues. So what we'll try to do, we'll try to uh, physically connect such that there is no ambiguity, there is no folding, right? So here, if you look into the addresses, as you can understand, I need to first select between the ROM1 and ROM2, right? So what we can do is that we can select that this bit, right? The 12 A12, right? So this particular bit and this bit, if we look into that, for ROM1 it's 00, for ROM2 it's 01. So I can use them, right? But can I? Because I have to make sure that I am not selecting a RAM as well, because the data bus, it's shared, right? It's shared among the ROM and RAM. So let us see. We had mentioned that the starting address for the RAM is 8000, right? So for in hex. So the starting address of RAM 1, what is it in binary? It's 1000000000000000, right? This is the starting address of RAM 1. So as you can see, I need to make my logic such that I I can select between the ROM and RAM first, and also between the ROM1 and ROM2, right? So let us design the circuit for ROM1. So if I have something like say A12, that means the 13th bit, right? A12 and A15 is the north of that, and then connect it to the chip select line. So and I'll make A12 A15 north, and then connect it to the chip selector, right? Now, what else I'll do? I'll make sure that it's working as the active high. The chip select is active. Here, as I was mentioning, now it's important, right? Because you need to make the logic, otherwise entire thing will collapse. Now let us see what I am doing here. For the RAM, as I mentioned, it start with 1000 and then something, right? So if my 15th bit is 1, so here I'm doing the not operation. So To the AND gate, I am sending 0 in the both here and here. If I am sending 0 to AND gate, the output is obviously 0. If your chip select is high, then obviously your at this addresses, so 1000 onwards, your ROM1 and ROM2 will never be selected. So your data line is safe, right? So you have to design something that your RAM1, RAM2, RAM3, RAM4, it will be selected appropriately, and then you can share the data line. So we'll come to that particular problem. Now, for so 0000H and onwards, we have already seen what are the addresses. But in these cases, what will happen? You'll see that when I have both my A12 and A15 as 0, I should select my ROM1, right? So A12 not, it should be 1, and then A15 not, it should be 1 if my A12 and A15 both the bits are 0. So my ROM1 will be selected and ROM2 will not be selected, right? Because A12 is 0, so this output of the AND gate will be 0, right? Similarly, 0001 and onwards. So what will happen? You are taking A12 as 1 and A15 not will be 1 again. So ROM2 will be selected for this address onwards. Hope this part is clear. I mean, I have again tried to be as much exhaustive as possible. Now what I have to do, I have to decide about the ROMs, right? So actually I could do one trick. What I could do is that actually, as you can see, right? So I can select any two bits now, and then can have two cross four decoders, and then can connect the RAMs appropriately. But let me write down the again starting address and stopping address of these RAMs also explicitly, because just for the understanding, we will not do these exercises again and again. Just for our understanding, let us again try to be a bit rigorous and then try to understand what is happening. So if you are getting the idea, probably you can go ahead and then write down the addresses. But let me be a bit slow and then write it down, right? So the starting address is 1000 FFF, sorry, 000. So what will be the N address? N address will be 1000 FFF, right? So 1111111111. That will be the N address for your um, RAM1. So what will be the starting address of RAM2? So the next address, right? Because we have sequentially tried to assign them. So the starting address, so it should be 1001 and then 00000000 and again 0000, right? What will be the N address? The N address will be 1001 1111111111. Okay. So what will be the? This is the end address, by the way, of RAM2, right? What will be the starting address of RAM3? So probably you have already picked it up, right? So it will be 1010, and from there and then 1011. this will be mm, 4, right? Now, as you have already realized probably that for selecting from RAM 1 to RAM 4, what I can do is that I can actually use um, this bit and these 2 bits, right? So I'll select these 2 bits first. So it's nothing but my A12 and A13, right? I'll put it to those 4 decoder, and then I'll have 4 lines, right? What I'll do next, I'll take A15 and then and with this outputs individually to make sure, because you have selected A12, right? So A12, you can see that I am using A12 here as well, right? So A12 is here as well, right? So I need to make sure that whatever I am taking out is actually from this decoder. So that will be only useful when my A15th bit is actually uh, 1, right? So I'm making sure by taking the AND operation. Right, so the first output will go to chip select of RAM1. The second output will go to the chip select of RAM2, RAM3, and RAM4. And that's the design that we want to have. Now there are 2 questions, 2 assignment questions. By the way, I'll not reveal the answer. It's up to you to think about. Now, in this particular setup or the design that I have made, is there any possibility that I'll have the overwriting problem, the folding problem? That means there is one address that can be accessed like multiple times, right? So, is there any problem of folding here? And the second thing is that I am using this 4 AND gates here. By the way, you should also realize that this is also some logical gates, right? So it's kind of a semiconductor gate that we use in our labs and all. So this decoder might also have some control. So given that particular assumption that your decoder might have certain controls, like so the types of controls that we are also talking about, can I actually drop these AND gates? So the question might sound a bit spurious, but if I tell you what are the controls, the answer will be straightforward. What I am saying is that there can be some select lines or some, so there is no read write for your decoder, right? But there can be some select lines for your decoder, chip select, right? So given that there is a chip select for your decoder, can I drop these AND gates or any other design if I assume that my decoder has a chip select line? So I'm assuming my decoder has a chip select line. In that case, can I drop this AND gates and uh, can have a different design that will give me the same kind of output that I am designing here, the addresses that I am designing here, but I'll just drop the AND gates. Is it possible or not? Right? So these are 2 assignment questions. One, if there is any chance of memory overwriting, that means folding. And the second, given my decoder has a chip select line, is it possible to drop the AND? Fine. So these are the ROM and the RAMs, right? Now there is again a third kind of memory. When I'm mentioning the word memory, now we should be very careful. So we'll not use the term memory because memory typically holds data or code or something, right? Now we'll try to introduce a third kind of memory in loose sense. As I said, afterwards we'll not call them memory. They are kind of memory because, as I mentioned, they hold some values, but they are known as the register. So what are registers? They are sequential elements that stores values. The important thing about register is typically your registers, they are inside your processor, and obviously as it's kind of memory, so and they hold different values, right? So what are these values? We'll look into that just after having a very brief discussion about the register. So your register, typically, if I try to talk about a 4-bit register, how is it different from the memory? So if you try to look into a 4-bit register, you'll see that there are two options. The first option is load parallel, and the second option is load serial. That means you can store 8-bit data in two fashions. You can load them parallelly, that means in one shot, or you can load them in a serial fashion, that means one bit after another bit, and you need a shifting to accommodate space for the coming bit, right? So similarly, you have actually different data lines. So you'll have parallel data lines. It's a 4-bit register, so I'll have 4 parallel lines, and I'll also have a separate serial line because I can load these registers serially as well. So here I'll have one line which will have a serial data communication. So I can load it serially. Right? Similarly, for the output, I'll have a control called output enable, and I can have a parallel output, or I can have a serial output. So as you can see, like registers are more flexible, right? So as you have seen in the last place, we had a read, write, chip select, this kind of control. But now we have additional controls, right? So I need to read and write as well, because when I'm saying that it will be loaded, that means the writing. And when I'm saying that there will be parallel output is reading, right? So reading and writing, that is there. Also chip select will also be there for register, but most of the cases registers are activated when the processor is active. But you can see that the registers are much more flexible than the memories. They are like, in memories you have slots, like thousands of slots stacking one after another. In registers, typically we used to have like one slots. Currently in different processors you can have multiple slots for the registers as well, but typically you'll have one slot. Like 4-bit means you'll have 4 places to store the data, but it's much more flexible. You can actually parallelly write the data in these locations. You can parallelly read, you can actually sequentially read or write. They are much more flexible, and as I mentioned, because of that, it's actually inside the processor. So processor needs to access these data very fast in different ways, right? Probably sequentially, probably parallelly, and that's why the registers are much more flexible. So In this lecture, whenever we are trying to talk about the memories, so if I mention memory, you should think about the external memories. That means the ROM and the RAMs that I had mentioned up to this point, right? And when I am talking about the registers, again, they are memory because they store value. Whatever stores value is actually memory, but they have a special name because their operations are different, right? So registers means the space that is inside the processor and that can actually hold data and can then process it in different ways, right? If you try to look into a processor, microprocessor, you'll see that at the heart of the microprocessor, you have something known as the ALU. That is the arithmetic and logical unit, ALU, which is connected to internal bus, internal bus line. Now, so whatever data or information ALU gets from your internal bus, it performs certain arithmetic and logical operations, right? So I hope you know what is arithmetic and logical operations. So we'll talk about them as well very briefly because I hope that you know already, but we'll talk about them. So after performing the operation, it puts the value back to the internal bus, right? But as I was mentioning that how will you know that what is the operation that you need to perform in the processor? So for that, we have certain very important things inside the processor. So the first thing that we have is the instruction register. What is the instruction register? It is also known as IR. So what is instruction register? It takes different instructions or piece of code and then it decodes, because we have mentioned at the very beginning that our processor, they only understand binary data, right? So the instructions are typically in different code format. It can be in C format, it can be like in Java or something, but you need to decode it. But whatever you do, the instruction first comes into the instruction register. From there, you have a decoder which generates several control signals. We are not drawing them explicitly because, say, for example, your instruction register might get some instruction called display, right? So there can be a code for display. Say, for example, just for now, assume that the code for display is 77. Say, right? Now, this will change depending on the processor. So this 77 will go to my IR, and then the decoding, when the decoding happens, it generates all the signals that will be necessary to initiate the task of my display, right? So after 77, probably I'll have a selection of the display device, probably display at this one. That means I want to display at display number one, because my processor might have several display option as well. And after that, there can be a value, so probably say 87, or there can be like some stored value I can also display, right? So say 77, this say R0. So what is R0? R0 is a memory location. So I can have memory registers as well. So R0, R1, R2. So these are your CPU registers. That means, again, these CPU registers are like the, as you can see, I was mentioning here, right? So you can have a single slots or you can have multiple slots, right? So these are like your memory chip that we were discussing so far, but it's inside the processor, right? So it's a CPU register. That means it's a memory block, but it's inside the CPU, right? So what I'm mentioning here is that probably I can say that display at display device one, the number 87, or I can say display at display device one, whatever is saved in R0. Again, this 77 is an arbitrary number or a code that I am writing here for microprocessors of different numbers or different architectures. We will have different codes. We'll look into that. Typically, we describe our code using words or numerical numbers, right? So it's nothing but display at this one number 87, and at the in a spec sheet you'll see that for display you have a particular code 77. That's why I am writing 77, this one 87, right? So when I'm saying that 77, that will go to the instruction register, and then you'll generate say probably hundreds of different control signals that will be required for your display work, right? So that is the purpose of your instruction register and the decoder. Along with that, you have some more things in a processor. Typically, as I said, like there are many different designs, but these are the components that will be there in any microprocessor, because that will be kind of the backbone of our microprocessor that we'll discuss in this particular course. So another thing that will be necessary is known as the program counter. Program counter that counts the line number or the instruction number that you are executing, right? Because it tracks what is the next instruction that I have to execute, as well as whether we have reached the last instruction, and then it will stop the execution. You'll also have the address bus and the data bus, right? So you'll have the address bus and data bus, so that you can actually store the values from the CPU register to the memory chips. You can take the values from memory chips to the CPU register and then can perform different operations, right? And also many times we'll have something known as the intermediate registers. That also connects with several different things, like it connects with the CPU register, it connects with the address buses and all. So what is the purpose of the intermediate registers? You will see that when I execute one particular command, it might happen that I need to store some values intermediately. For example, say my ALU will add two numbers, right? So addition is a binary operation, right? So it might happen that I need to store the first number and then I have to fetch the second number and then have to add them. Or it might happen that I need to store the intermediate number or the operation somewhere, right? So typically we'll also have some intermediate register sets which will store the numbers temporarily in between the operations, the arithmetic and logical operations that we are doing. In between we can store them so that we can have the binary operations or the ternary operations seamless, right? So that is different from your R0, R1, R2, because R0, R1, R2 will fetch the data or probably store the data even after the operation is complete. So say for example, if I want to have an operation R2, R0 plus R1, that means I'll store whatever is the value inside R2 after performing the addition operation of the values that are stored in R0 and R1. So when I try to do it, you'll see that there are different instructions that will appear. So it will be like add R0, R1, R2. So what is this? I am giving the, again for add there will be a particular code. So probably say I'm now assigning arbitrarily, so probably say 60. Right? So 60 R0 will have one per number, R1 will have another number, R2 will have another number to indicate. But say 60, right? So that will be the addition. So what I'm saying, I'll add R0, R1, and then I'll store it to R2. So there are several things that I need to do, right? So I'm sending the add command to the instruction register. So it will activate all the control signals that will be required for my addition. Then I'll take my R0. So R0 will be read. Now what I have to do is that I have to keep it somewhere, right? Because now I have to fetch R1 as well, because your instruction register will generate the decoder signal one by one. So your ALU cannot store anything, right? So ALU will just add. It's kind of the adder, for example, right now. Imagine it, the ALU as the adder, right? So ALU does not have any memory. It will just perform the operation. Now the decoder signals are such that the ALU is now like an adder. So in instruction register will actually fetch the R1, but by that time the R0 will be lost if you are not keeping it somewhere. So the R0 will be kept in the intermediate register, will fetch R1 and then perform the addition operations, right? So there can be one intermediate register, there can be multiple intermediate registers, but the difference is that when you are starting the operation, so when I start the add, right? So I'm inside one code, I'm executing it. Now when I'm doing the operations, I have to keep them somewhere, right? I cannot keep them in the registers. I have to keep it somewhere. For that, I have some intermediate registers where I keep those values and then perform the operations, right? After doing that, I'll get back to my CPU registers R2. So it will write it down to R2. So after that, I can have again one set of instructions. Say, for example, I can have write R2 1000. What is that meaning? That means I'll write the value of R2 to the memory location 1000. This is the external memory. So my processor can have some external memory. So whatever is in R2, so I'm adding it, I'm storing the value that I'll get after performing the operation R0 plus R1. It will be stored into R2. Now I'm storing it permanently to my external memory at location 1000. Right? So there, as I said, like there can be many such operations. We'll look into them. But the schematics, the idea is that the first thing, the take-home messages are like there is something called the register, which are different from the memories that we are talking about up to now. They are much more flexible. Typically, when we talk about registers, they are inside our processor. There can be, as you can see, there can be instruction registers which are dedicatedly there for finding out what is the command or the instruction that I want to execute. There can be intermediate registers which will store the value once I am inside one code block when I am executing one command. There can be CPU registers which will store the value when you are you know performing the operations inside the processor. There can be memories, external memories as well, right? Additionally, we can have something called the program counter. We can have decoders. We also have the ALU, which is the heart, as I mentioned already. We can also have something known as the flag, so which is attached with the ALU and also with the internal bus. What is the purpose of the flag? The purpose of the flag is to track the process. For example, I hope all of you have seen some coding errors, right? So for example, if you try to add let's say my name is Shomik, right? So if you try to add Shomik plus 11, right? Now, if you are not converting Shomik to some number using ASCII or any other coding, this addition should not happen, right? Because these two things are from different domains. This is kind of a string. This is integer. They should not add, right? So how will you know that it's a valid exercise or not? How will you know that whether you have performed something like 1 by 0 or say 0 by 0, right? So there are different flags or indicators to track the special cases. For example, if there is a carry in the additional operation, you have a special scenario, right? So the flag will generate different values and give ideas about the special cases. For example, if it is like 1 by 0 scenario, you will have one flag value. If it is a 0 by 0 scenario, you will have a different flag value. If it is a carry addition, after addition, if you have a carry, you will have a different scenario. So your flag will give you, cases that will help you to understand what is happening inside the ALU, or if there is any error, and accordingly you can debug the program, right? So it's kind of a debugging tool which will give you an idea that whether everything is going fine or if there is a special case, and you can understand, okay, there is something wrong that I need to fix, right? So we'll look into flags as well, but there are different components right inside the processor which will help us to perform different operations. So from the next class we'll try to look even more closely to a particular processor which is the 8085 processor, and there we'll try to understand these different components like the instruction registers, the CPU registers, the ALU flags and everything, right? So we'll stop here for today. From the next class, we'll start discussing about the 8085 process. Thank you.